Hello, everyone. Welcome back to our journey through thermal physics. Let's start with a question. Have you ever noticed how your pressure cooker starts whistling when the steam builds up? Or how scientists can measure temperatures far beyond what mercury thermometers can handle? Well, that's because gases don't lie. Unlike liquids, gases at very low densities behave identically no matter which gas you use. Whether it's hydrogen, helium, oxygen, or nitrogen, they all expand and contract the same way when heated or cooled if made dilute enough. Now, every gas is described by three key quantities: pressure, represented by the symbol P, volume, represented by V, and temperature, represented by T. These three are inseparable friends. If you change one, the others immediately respond. Together, they define what we call the state of a gas, and their relationship forms the basis of one of the most elegant equations in physics, the ideal gas law. As you can see in the diagram, a gas thermometer uses changes in pressure to measure temperature, simple yet incredibly reliable. Now let's meet two pioneers who laid the groundwork for understanding gases, Robert Boyle and Jacques Charles. Boyle's law says that if the temperature of a gas is kept constant, then the product of its pressure and volume always stays the same. In symbols, we say P multiplied by V equals constant. So, if you squeeze the gas to half its volume, the pressure doubles, and if you let it expand to double its size, the pressure drops by half. Next comes Charles' law. It states that if the pressure is constant, the volume of a gas is directly proportional to its temperature, provided the temperature is measured in kelvins. In symbols, we say V divided by T equals constant. That means if the temperature doubles, the volume doubles, and if you cool the gas to half its temperature, its volume shrinks by half. Both these laws describe how gases behave when one condition is held fixed. Combine them, and magic happens. We get the ideal gas equation. Let's now combine what Boyle and Charles discovered. When you merge the two relationships, you find that the ratio of P times V divided by T remains constant for any fixed amount of gas. This leads us to the ideal gas law, which is written as P times V equals mu times R times T. Let's break that down. P is pressure measured in pascals, V is volume measured in cubic meters, mu, the Greek letter mu, represents the number of moles of gas, R is the universal gas constant, equal to 8.31 joules per mole per Kelvin, and T is the absolute temperature in kelvins. So, 1 mole of any ideal gas at standard temperature and pressure, that's 0 degrees Celsius or 273.15 Kelvin, occupies 22.4 liters. The beauty here is, no matter which gas you choose, this law holds true under normal conditions. Whether it's the air in your car tires, the helium in a balloon, or the fuel gas in a rocket engine, they all obey this simple but powerful relation: P times V equals mu times R times T. Now, let's imagine a gas trapped in a sealed, rigid container, so the volume V stays constant. If you start heating the gas, its molecules move faster and collide more often with the container walls. That means the pressure P inside increases. This gives us the relationship: pressure is directly proportional to temperature if volume is fixed. In simple words, when temperature goes up, pressure goes up. When temperature drops, pressure drops. This principle forms the basis of a constant volume gas thermometer. If you plot pressure on the vertical axis and temperature on the horizontal axis, you get a perfect straight line. And if you extend that line backward, it cuts the temperature axis at a point where pressure would become zero. That point corresponds to minus 273.15 degrees Celsius, the lowest possible temperature, where molecular motion would theoretically stop. We call that temperature absolute zero, nature's coldest possible setting. Now that we've met absolute zero, let's build a new temperature scale around it. The Celsius scale is convenient, but it's based on water's freezing and boiling points, not on nature's true zero. So scientists defined a new one, the Kelvin scale, named after Lord Kelvin. The relation between Celsius and Kelvin is simple: T equals T sub C plus to 73.15. That means if you take a temperature in Celsius and add 273.15, you get its value in kelvins. So, 0 degrees Celsius equals 273.15 Kelvin and 100 degrees Celsius equals 373.15 Kelvin. In the Kelvin scale, 0 Kelvin is absolute zero, where molecular motion stops completely. This scale makes all gas laws simpler and universal, no negative numbers, no confusion. That's why in physics, we measure temperature in kelvins. It's the absolute truth of thermal energy. Alright, let's try a quick example to bring this to life. Suppose we have a gas that occupies 2 liters at 1 atmosphere pressure and a temperature of 300 Kelvin. What will be its new pressure if we reduce the volume to 1 liter, keeping the temperature constant? We use Boyle's law, which says P1 times V1 equals P2 times V2. Now substitute P1 equals 1 atmosphere, V1 equals 2 liters, and V2 equals 1 liter. So, 1 times 2 equals P2 times 1. That gives us P2 equals 2 atmospheres. Hence, when the volume is halved, the pressure doubles, simple and satisfying. You see this every time you pump air into a bicycle tire. As the air is squeezed into a smaller volume, its pressure rises, making the tire firm. Let's wrap it all up. The ideal gas law, expressed as P times V equals mu times R times T, unites all the individual gas laws into one universal formula. It shows that pressure, volume, and temperature are interdependent and helps define absolute temperature through the Kelvin scale, which starts at absolute zero, minus 273.15 degrees Celsius. This concept forms the very heart of thermodynamics. From car engines and pressure cookers to weather balloons and space probes, the same law explains it all. It's amazing to think that something so simple, just 3 variables, P, V, and T, can describe everything from a party balloon to the atmosphere of Jupiter. So next time you inflate a ball or boil water, remember, the gas inside is following a rule written by nature herself: pressure times volume equals moles times the gas constant times temperature. That's the beauty of physics, finding universal order in everyday experiences. I hope this session helped you feel the pressure in a good way. See you in the next class, where we explore how materials expand when heated. Until then, stay curious and keep the physics flowing.